So last time I started showing you how incredibly constrained the three particle amplitudes for massless particles are. They're completely determined just by symmetries, just by translational invariance, which for the three particle kinematics told us we were in this very special configuration where either the lambdas were parallel or the lambda tildes were parallel. There are no obvious kinematical invariants, and everything is completely determined once you give the spins of the particles. So that's quite remarkable. Up to the strength of the coupling constant, you can just write down what three particle amplitudes are just from symmetries. Then dynamics enters when we imagine what the four particle amplitudes can look like, and we make this assumption of weak coupling, which means that we work in some leading approximation where the 2 to 2 amplitude only has poles, and then we get to input directly the physical principles of locality and of unitarity. As locality tells us where the poles of the amplitude can be. The poles can only occur when either S or T or U goes to 0. And unitarity tells us that the amplitude has to factorize on those poles into the product of two lower point amplitudes, which are just the three particle amplitudes that we fully determined. Okay, and so there's a very clear strategy then. Can you write down consistently factorizing four particle amplitudes? Naively, it's trivial because all you do is compute what the residues are in any channel by multiplying the three particle amplitudes. And then once you figure out the residue, you just multiply by 1 over S in the S channel, 1 over T in the T channel, 1 over U in the U channel. That strategy works very nicely for all the simple theories, like phi cube theory, or even the Yukawa theory. And all these theories, which from the Lagrangian point of view don't involve any subtlety or complication of gauge invariance, gauge redundancy, and so on, are reflected in the amplitudes by the fact that the corresponding three particle amplitudes have no denominators. They don't have any poles. And so the strategy of building consistently factorizing 4-point amplitudes is trivial. But exactly for the theories that are interesting, Yang-Mills and GR, the three particle amplitudes have poles. It's quite mysterious that they have poles. That's a reflection directly in the on-shell amplitudes of the slight whiff of non-locality associated with these with gauge theory and gravity. And so it's non-trivial. It's non-trivial to build consistently factorizing four particle amplitudes. And we found that I went through one example of just a single particles of spin S interacting with each other. And we saw it was impossible to have self-interacting particles of spin S. A single one, unless the spin was 0 or 2. And if we allowed many of them, you could also have spin 1, but the spin 1 couplings had to be precisely the ones given by Yang-Mills theory, where the strength of the interaction, where the FABC had to satisfy the Jacobi identity. And you can go on in this way. So I'm not going to spend the whole lecture doing more and more of these analysis. You got the idea and what the non-trivial point is. But continuing in this way, you can discover that the only possible interacting theories of massless particles you can have are theories of spin 0, a half, 1, 3 halves, and 2. You can't have higher spin particles if gravity exists at all. Simply the interaction with gravity makes their existence impossible. If you do have gravity, then you can only have a single graviton. You can't have more than one graviton. You can have at most 8 massless spin 3 half particles, and if you have them at all, they're supersymmetric, and you discover extended supersymmetry if you have more than one of them. Okay, so that's really a remarkable thing, that directly from the physical principles, with no veil of formalism of introducing fields or this or that, and redundancy and gauge fixing, we don't see any of that. We don't need any of that. We go directly from the principles to the physical observable. And not only do we conclude which theories are consistent and which theories are not, we actually compute the amplitudes at the same time, right? So we just wrote down in one line the amplitude for 2 to 2 graviton scattering that, as I told you, if you tried to do it in any direct way, good luck. Okay, it's a horrendously complicated calculation. No, I do not. No, I did not mention loops. I was just talking about trees. I'm probably not going to mention loops. Instead, today I want to. Yes.
Statement about higher spins would not apply if you have ideas.
That's right. So here we really assumed Poincare symmetry. Okay, so we assumed Poincare symmetry and Yeah, consistent factorization in flat space. As you know, all those self-interactions in ADS disappear in the flat space limit, so you get non-interacting theories.
Last time we talked about the spin one scattering, and you talked about the structure functions and how the Jacobi identity.
That's right.
But does it point to the underlying Lie algebra?
Well, I mean, any FABCs that satisfy the Jacobi identity give you a Lie algebra.
Right.
So that.
Does it
No, of course not. No, absolutely not. So these arguments don't tell you which. So it restricts the description of the world to some gauge theory based on some Lie group coupled to gravity, possibly with supersymmetry. Okay, that's what we discover from these arguments, right? And yes.
It means that those biometric gravity.
Crap. Absolutely. Yes. Very easy. Yeah. Yeah, that's yeah. So there, not everything goes. In fact, very few things go, and that one most certainly does not go. Okay. Sorry.
What did he say?
The theories with two massless spin 2 particles by gravity. They're called various things. They're just crap. Okay. So what I want to do today, because as I told you, I wanted to just do some practical things in these lectures. I want to talk about how this is extended to the massive case. Okay, so first I want to talk about now massive amplitudes. And remember, our formalism, when the particles are massive, is just slightly decorated. Now we have P alpha alpha dot equals lambda alpha I, lambda tilde alpha dot I, where I runs from 1 to 2. Or plus and minus, okay, and there's an SU2 little group acting on this I index. Okay, and if we have a massive amplitude for any leg, it's supposed to be this 2s symmetric tensor in these indices. So it's going to depend on the lambda I and the lambda tilde I for that particle. Okay. And already last time we gave some examples, Compton scattering, just some examples of what these amplitudes look like, but now I want to return to thinking about determining the 3 particle amplitudes. Now we want to do the same thing we did for massless particles, but for massive particles, and determine the, and start thinking about what the 3 particle amplitudes are. Okay, so and I'm going to do, again, just the sample of some of these. Just we won't do everything systematically. If I have some time left over, at least in the last half hour, I want to tell you how all these things have analogues in cosmology, since that was in the title of my lectures. So we've already done the case of 3 massless particles, so let's do the first new case. 2 massless and 1 massive. And again, this is something, if you care about sort of collider physics, and you wanted to know how you would compute, I don't know, the cross-section for a resonance of a spin 7 particle coupled to gluons. Again, if you're scared or you think you've got to find the Lagrangian, give it to MadGraph. No. Okay, we're just going to write down the answer in one line. Okay, so I'm going to imagine that I have some massless particles of helicity H1 and H2 and some massive particle of spin S. And I want to write down this amplitude. Now, this is also going to turn out to be unique. Okay, so this object is going to be unique. So this thing has a bunch of has 2s indices, I1 through I2s. I'm going to find it convenient. It's not necessary, but it's just slightly easier to think about. Is this mi1 through I2s? That it has to have a bunch of lambdas. Now, it can have lambdas or lambda tildes, right? Because both lambda and lambda tilde carry the I index. But remember, we had that p lambda equals m lambda tilde. So we can go back and forth between lambdas and lambda tildes using p. So that means that if I want, I can just choose lambdas. Okay? Any expression that had lambdas and lambda tildes, I can convert it to an expression that only has lambdas. So I'm going to do that. So I'm going to write this as lambda I1 alpha 1 through lambda IS alpha S. That's just going to make manifest that it has all these indices. And then there has to be something that contracts all these alpha indices. okay? Which is also totally symmetric. So this is going to be totally symmetric in these guys, so this has got to be totally symmetric in those guys. Yes?
You're not writing the piece?
Sorry?
Shouldn't there be piece?
No, there might be p's all over the place, but we have to have these indices, right? So that's what I'm saying. We have to have these indices, so anything is going to has to have these symmetrized indices. It might have lambda tildes, but it doesn't matter. Everything I can write in the end purely in terms of lambdas, okay? So now I'm going to write down this object. In the end, for the actual amplitude, I'll be contracting with these lambdas, okay? Okay, so what can we write down? Well, see, now it's really simple. I have to get alpha indices. The only things that have these just alpha indices now are the lambdas for these guys. Okay? So what can I do? I have to have some number. So now I have some here. I have some alpha 1 through alpha 2s. Oops. This is 2s. Sorry about that. Okay, well, I can have some number of lambda 1s, alpha 1, blah, some number of lambda 2s. That's all I can have. So the total number of them has got to add up to s. So what I can have is lambda 1, I can write it like this. S plus h2 minus h1, lambda 2 to the s plus h1 minus h2. And then I can okay, so let's look at, so this is a unique answer, right? So let's see why this is. So what do I mean by this expression? This thing really has, again, a stack of alpha indices. I'm just not writing them down because there's no point in writing them down, right? So I have this many lambda 1s, this many lambda 2s. Now notice, because this particle is massive, the angle brackets, square brackets no longer vanish, right? 1, 2 times 1, 2, p1 dot p2 is actually m3 squared. Okay, so this is not gonna, this does not vanish. So I'm just writing something down that has the right number of indices, but anything, but I can also write down, either the square bracket or, again, the angle bracket and the square bracket I can trade for each other because of this. Okay, so the most general expression I could write down is lambda 1 to some power, lambda 2 to another power, and let's say square bracket to a third power. And then I fully determine the powers just by the requirement that the sum of these two things is equal to 2s, and that the weight of particle 1 and particle 2 works out correctly. Okay, so this is the unique answer.
Sorry, which two things?
So I have particle 1 and 2. So the most general expression I can have is lambda 1, the most general expression I can have is lambda 1 to the A, lambda 2 to the B, 1, 2 to the C. Okay, what this really means, but there's a bunch of indices. And so I have to have A plus B equals 2s. I have to have A minus C equals minus 2h1, and B minus C equals minus 2h2.
I'm sorry,
okay?
The first condition, where is it from? The second and third, I understand.
The first condition is simply that I have to have 2s indices.
Okay.
I have to have a total of 2s indices. Okay, so I have these things, and I just solve for A, B, and C. All right? So this is the answer. Again, up to an overall coupling constant. This is the answer. And again, that's pretty cool. You didn't have to write down a Lagrangian, blah, blah, blah. You can just directly write down this answer. Now, already from here, we get various sort of famous facts very, very quickly. Let's just comment. Hey, Tomer, how you doing, man? Yeah, long time no see. You're looking good. All right. So for instance, there's something a little amusing. Let's say that these particles have opposite helicity for a second. Okay, so let's say that h1 equals minus h2. Then I have lambda 1 to the s, minus 2h1, lambda 2 to the s plus 2h1. Okay, and then, but you see, this is not going to make sense if s is smaller than 2h1. Okay? This vanishes. It's impossible. So we learned something very interesting, that I can't, if I have a massive spin if I have a massive spin 1 particle, let's say, a massive spin 1 particle cannot decay to 2 massless spin 1 particles of opposite helicity. Okay? Sorry? No, here, this is nothing to do with unitarity. This is just the Poincare symmetry, nothing else. Okay?
Why does it not make sense if S is less?
Oh, because I just can't, I don't have enough indices here. So, I mean, these numbers have to be positive, right? Because I have to have a positive number of lambda 1s. Okay? Okay? Now, furthermore, so you know where this is going. This is Yang's theorem, right? Furthermore, if the particles have equal helicity, then you'll notice that if S is odd, particles have equal helicity. If S is odd, this thing has the wrong Bose symmetry under interchange of particles 1 and 2. Now, from this point of view, if I had longer, I would explain to you how we derive spin statistics like this. Okay? And in fact, but let me quickly tell you how you derive spin statistics from these arguments. You derive spin statistics by imagining what the scattering of these particles looks like with gravity. And as we saw crucially last time, when you have gravity or Yang-Mills theory, you can't just add the channels together. You have to compute the residue in some S channel, and then it forces the existence of residues in another channel, and then you get what you get. It either works or it doesn't work. So in the context of gravity, for the scattering of particles of any mass against a graviton, you discover just from one channel that it's forced to have the statistics of picking up a minus sign when it's a fermion and not when it's a boson. And everything else is inconsistent. Okay? So we can even discover spin statistics from consistency of scattering with gravity. That shouldn't surprise you. It shouldn't surprise you that we have to invoke scattering with gravity in order to get answers that we normally get from locality in standard quantum field theory, standard Lagrangian arguments, because locality in a standard Lagrangian is what allows you to couple the system to gravity. So if you're going to see the same arguments from an on-shell point of view, you want to see the consistency of scattering against the gravitons. Okay, so we can even derive spin statistics even internally from these arguments. But anyway, once you have those arguments, then you cannot have an odd spin particle decay to anything with the same helicity. And the combination of those arguments tells you that you can't have a massive spin 1 particle decay to 2 massless spin 1 particles of any helicity. When it's opposite helicity, it's simply impossible. When it's same helicity, it would violate Bose symmetry. Okay? And you see how important Lorentz invariance is for this argument, because simply rotational invariance does allow it. Okay, so that's, again, the sort of famous thing about Yang's theorem. And the analog of this statement is for a massive spin 3 particle. A massive spin 3 particle cannot decay to a pair of gravitons. Okay, so it's exactly the same argument. Okay. Yes?
How do you know that because it's a scattering with the sign will also scattering with scalar?
No, because the whole point is that it's a coupling to gravity that defines what you mean by a species of particle. Okay, because it has a universal coupling. So then whatever other indices you have for the particles, you see that the scattering of gravitons tells you that when you interchange them, you pick up a plus sign when they're bosons and a minus sign when they're fermions. Yes?
It's not with a different instead of Poincare symmetry, would you still get some kind of a spin statistic?
No. Oh, sorry. No.
There is spin statistics only for Poincare?
Yes, absolutely. Absolutely. It's a crucial, Lorentz invariance is absolutely crucial. In quantum mechanics, nothing forces it on you. Yeah. No, I mean, in this formalism, that's how it comes up. But we also know that it's not forced on us without relativity. Okay? Anyway, so that's 2 massive and 1 massless. Yes?
This construction is limited to 4 dimensions.
Well, and what I was talking about here for simplicity is in 4 dimensions, but all of this really holds for any number of dimensions.
So the relationship with spinels in this SL2, that's just...
That is just in 4 dimensions. But there's an extension of it in any number of dimensions. It's a little more complicated. But, sorry?
The conclusion, for instance, about spin statistics.
That's right. If you go to lower dimensions, it's more interesting. So, but for example, you immediately discover, you immediately see in doing things this way that in 3 dimensions for massless particles, you don't have spin. You only have bosons or fermions, for example. How you see anyons is a little more interesting. But anyway, yeah, let's just stick, we're just sticking mostly with 4 dimensions, but one can extend and think about these things in any number of dimensions
So in
as
our
well.
latest calculation was like, as general, aside from adding Lorentz invariances, sorry, we had like the n squared and the p1 times p3, which you can always add, right?
Sorry?
I mean, we got like a result, but you could multiply that by n squared over p1, p3, right?
But P1, P3 is also m squared. Everything is m squared. There's no Lorentz invariance. Everything is just given by m squared. Exactly. Yes?
Is there any reason why you can't build a local Lagrangian out of these spinor helicity guys? Like these could be the polarization vectors?
Yeah, that's right. You can, I mean, that's one sort of practical thing that you can do. From a Lagrangian, you can express the polarization vectors in terms of spinor helicity variables, and from a Lagrangian, following the Feynman rules, get these answers. You can do that. It's just, why bother? You can just write down the answer directly anyway. Okay, so anyway, so that was the 3-particle amplitude. Just to write it down, the actual amplitude, when we contract with everything, 1, 2, 3, can look like 3 bar 1 to the s plus h2 minus h1, 3 bar 2. This is just trivial. I just contracted it with the lambda 3 just so we have the actual amplitude with the little group indices. Okay. Okay, yes.
So there's some, if I turn off gravity,
Yes.
there's some, the distinction between locality and factorization, and with factorization and unitarity is a little blurred in the on-shell.
No, it's not. The only there's a very clean distinction between there's a clean statement where the poles are and what has to happen on the poles. Okay, so that's the invariant thing, is that you have to have the poles as st and u go to 0, and on those poles the amplitude needs to factorize. The words that you wrap around those facts are the closest words to where the poles are is locality, and the closest words to the factorization is unitarity. But as you see, it's sort of one statement. They're kind of wrapped up together. It's hard to disentangle them. Yeah.
That's my question.
But it has nothing to do with the presence or absence of gravity. That's equally true with or without gravity.
So it doesn't make any difference.
No. No. Yeah.
My question. So if you look at the particle data
Yes.
table, there will be limits on the Landau-Yang forbidden decay.
That's right.
Okay. So presumably, if you're looking for that forbidden
Yes, yes. Right.
you need some kind of an extension of the theory that will allow.
That's right, and that's very easy to do. In fact, this is very nice. I was just going to say, this is a very nice exercise for the students. How in this formalism do you write down an amplitude that would actually give you z decay to 2 photons? Okay? And the answer is you can still use this formalism, but the fact that you need to break Lorentz invariance, and it's still a useful formalism, it keeps track of helicity and everything, but the fact that you don't have Lorentz invariance means that you're allowed to contract the lambda with the lambda tilde. Okay? So if you allow yourself to contract the lambda with the lambda tilde, you break SL2 cross SL2 only down to the diagonal SU2, which is rotations. So that's an exercise for you. Write down an object that is a legal amplitude, but which involves contracting a lambda and a lambda tilde. Okay? And that's what and that's the Lorentz violating amplitude for z to 2 photons. Okay? And in fact, when you write down that object, you learn sort of more things. You've picked out a frame. So the amplitude actually depends on how boosted the z is. And so there's various things about this process that are sort of more interesting than the limits that are there in the literature, which actually involve how boosted the z is and so on. And you can get the answer directly from this formalism. That's a nice exercise for you.
And physically,
Okay.
does it mean, can, for example, a background field violate Lorentz invariance?
It could, of course, if you literally do it like that, you would have, because the underlying theory is Lorentz invariant, you have to be relying on the presence of some higher dimension operator that would make this thing happen. Alternately, you would not think of it as z decay. You'd think about it as z banging into a photon and giving you some interesting final state, which is allowed. Okay? Okay, so, all right, so now let's go to the next interesting case, which is 2 massive and 1 massless. So any questions about this? Okay. All right, good. So let's go to the next interesting case, which is, and it's the last one I'll really do, is 2 massive, 1 massless. we'll leave all massless. Is not as interesting, actually. Okay, so once again, so let's say I have, so I'm going to have particles 1 and 2. They have spin s1 and s2, and particle 3 has some helicity h. So I'm going to have some alpha 1 through alpha 2s1 for this guy, and some beta 1 through beta 2s2 for this guy. Okay? And again, I'm going to contract. So I'm doing the same thing I did before. So I have to contract these with lambda 1 and these with lambda 2 to get the little group indices. Right, in the end. Okay, now. Now, what I can do, I need to somehow have an object that has these indices. Right? What do I have that has these indices? Again, only lambda 3. Okay, but I can build a basis, a basis of all two-dimensional vectors with this alpha index in the following way. So let me define a two-dimensional basis. So a 2D basis. Let me call it U alpha is, let's say, just lambda alpha. This is lambda for particle 3. And V alpha is P3, this is lambda 3, P3 alpha alpha dot lambda tilde 3 alpha dot. Maybe I put an over M here. Well, maybe I'll just leave it like that. Okay? This is a U and a V. Let me see if this is actually a basis. Okay? Sorry. I'm at P1 here. Okay? Notice by momentum conservation, if I'd used P2 instead, I'd just get the same thing up to a minus sign. Okay? So let's actually see if it's a basis. So I'm going to look at the inner product of U and V. And this inner product of U and V is nothing other than P3 dot P1, let's say. And this, in turn, is nothing other than M1 squared minus M2 squared. Okay. So if M1 is not equal to M2, the particles have a different mass. This is a perfectly fine basis. And so now I know that I can make any object that I want just by writing down a bunch of U's and V's. I just have to write down the correct number of U's and V's so I get the correct number of indices for all of these guys. Okay? So now there isn't a unique structure. Okay? Now I can have a number of structures, but now the most general three-particle amplitudes that I can have are just some number of U's and some number of V's. And the total number of U's minus the total number of V's is determined by the helicities of the particle. Okay? Because U has little group weight -1 and V has little group weight +1 for the massless particle. Okay, so those are what the three-particle amplitudes look like for two massive and one massless when the masses are different. Okay, so if you want to know, you have a massive spin 3/2 particle, a photon, a massive spin 1/2 particle. Let's say we want to do that example. Okay, so let's say we have massive spin 3/2 and a photon and massive spin 1/2. Then I can have actually I can have two structures. I can have U, 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 V. So let's call these indices here beta 1, beta 2, beta 3, and this is alpha 1. Okay, so I can have 3 U's and a V. If I have 3 U's and a V, that corresponds to this guy having helicity minus. Okay, because so here I'd have U beta 1, beta 2, beta 3, V alpha 1. And another structure I can have is U beta 1, U beta 2, V beta 3, U alpha 1. Okay? And that's it. These are two structures. So I fully symmetrize in the betas, fully symmetrize in the betas. Okay, so we see that massive spin 3 halve, that's the example I was talking to you about in the first lecture. You know, some funny spin 3 halve excitation of the top quark decays to a photon and the top quark. There are two structures that you can have, and here they are. So there's G1, let's say, and G2. And once again, we can contract them with the corresponding lambdas to get the actual amplitude. So the actual amplitudes would be like G1. I don't know. This is particle 1 and 2. We could have G1 like 1 bar 1 bar 3 cubed 2 bar 3. Sorry. 2 bar 3 plus G2 1 bar 3 squared 1 bar 3 2 bar 3. Okay?
Why did you move to the U and the V? Why didn't you use lambda lambda 2? What did this get you?
No, because I'm not moving to anything. I need to have these just alpha indices, and I only have one object that only has the alpha indices, which is the lambda and lambda tilde for the massless particle. So because I have to write things in terms of alpha indices, I need to find, in order to write the most general thing down, I need to find a basis. And this is a basis of two-dimensional vectors. Okay? Yes? Three V's and one U, it would be for the opposite helicity for the photon. Okay? So you see that what's fixing the net number of U's and V's is the helicity of the photon. Okay? All right. So again, yes?
Can you determine from this amplitude the dependence, for instance, of the decay width on the mass of the...
Of course. Yes, of course.
How does it look like?
Well, you just mod square and figure it out. I mean, this is the amplitude, so we can figure out what the width is from yeah.
On top of what you can get from just dimensional arguments.
Of course, yes. This is the actual amplitude. So you just mod squared and you get the answer, right? Yes, yes. Yes.
That decays to a proton.
Yes, yes.
Plus pi.
Yes.
Massless pi.
Yes, yes.
So what would you get the dependence on the mass of this object?
I don't know. We'd have to do it, but it's the amplitude. You just mod squared and you get the answer. I mean, you get the angular dependence, you get everything. Okay. So anyway, so that's what happens when you have two massive and one massless when the masses are different. Okay? And again, once again, you might have been frightened of this calculation if I asked you to figure out the coupling between a massive spin 3 blah, blah, blah. But anyway, it's complete triviality, right? Okay, now let's move to the slightly more interesting case of two massive and one massless.
There's a way to predict G1 and G2 that
No. These are from here we see that there's two structures now. No, it's no longer unique, right? So now there are two structures you can write down, but there's a finite number of structures, okay? And you just work them all out. Okay, now let's do the more interesting case, so the more physical case. That's more familiar when the masses are equal to each other. Okay, so now this is something a little more new and interesting. So what happens if M1 equals M2? So this is equal mass and what we call the X factor. So let's say we have two equal masses and, again, a massless particle of helicity h.
Are these particles identical?
They don't have to be, no.
Just masses.
Just the masses are identical. They don't have to be identical. Maybe there's some degeneracy in the spectrum. They don't have to be the same particle. Okay? And actually, before doing anything else, so first of all, we have this issue that we don't have a basis anymore, right? So now I have U alpha, which was lambda alpha, and I still have V alpha, which is P lambda tilde alpha. but UV is equal to 0. Okay, these guys are parallel to each other. Okay, so that's one issue. But actually, let's do something even simpler to begin with. Let's say this guy's just a scalar. All right, we don't even have any indices. What could the amplitude possibly be? Okay, so this is a nice question. This has to be something of units of mass. So, sorry, m1 is equal to m2. So m and m. It has to have units of mass. But it has to have the helicity weight of this photon. Let's say it's a photon. Helicity minus 1 or plus 1, right? What could it be? We don't appear to have anything which has the correct weights. Right? You have to have something that carries helicity weight. But in fact, these problems are very closely related to each other. You see, it's true that now in this two-dimensional space, we're not filling out all the directions of this two-dimensional space. Everything is in the direction of u, lambda. Lambda and p lambda tilde are in the same direction. But we have one tiny bit of extra information. What is the constant of proportionality between v and u? The whole point is that they're proportional to each other, right? So, in fact, we know that p lambda tilde is proportional to lambda. So let me call the constant of proportionality x. Okay? Now, notice that this object x has helicity weight 2. Okay? Because it translates between a lambda tilde and a lambda. And therefore, what is this amplitude? It's just m times x. Okay. So the three-particle amplitude for just two scalars and a photon is m times x. What about the other one with the negative helicity guy? It's m x inverse. Okay? Sorry, times the charge, of course. There's some overall coupling constant. All right, let's do another example. Let's keep going. Let's say we have a massive spin-a-half particle, electron, but with equal mass. Now what can I have? Now I have an alpha and a beta here. Okay. Now the structures that I can have is Em epsilon alpha beta times x. That's one structure that I can have. There's another structure I can have, plus just lambda alpha, lambda beta. It's lambda for particle 3. Okay, so let's say I'm doing, if I'm doing helicity minus here, let's say I do that one. Okay, so that's Em x inverse. Okay? This one, it has a name. It's the electric charge. What is the name of this one? Anybody? It's actually directly G minus 2. Okay? Right? So the, not G, it's directly G minus 2. Okay? So the anomalous magnetic moment is not some funny feature of what the electron does in the magnetic field. It has a completely sharp definition. It's one of the on-shell definition. It's one of the two structures that you're allowed to have for the three-point coupling of an electron. Okay? And in general, if you have a massive spin-s particle, oh, sorry, what's the coupling to gravity? What's the coupling to gravity? It would be just have different units, 1 over m Planck, m squared x to the minus 2, epsilon alpha beta. Okay, so that's the coupling to a graviton instead. Okay, and then we could have this guy too, and that's some analog of a gravitational G minus 2. Okay, so we can have a gravitational G minus 2 as well. Yes?
Sir, but why does x carry the helicity?
Sorry? You see it from this expression, because p lambda tilde is mx lambda. So lambda tilde is helicity weight 1, lambda is helicity weight minus 1, so x has to have helicity weight 2.
But that means that x transforms accordingly when
It does. X has weight too under the little group, which is good. That's why we can use it to keep track of the little group of the massless particles here.
What is X? I mean,
X is a constant of proportionality between U and V. Okay.
it's not a number, so
It's not a number. No, it's not a number. It's something it's not a number. That's right. It has little group weight. If you do a little group transformation, X picks up a phase.
So suppose I want to write down the physical scattering.
Very good. You see, so you could have asked me this question long ago. It has nothing to do with this particular problem. The amplitudes change when you do Lorentz transformations. They pick up phases. Those phases go away when you mod square. Okay, so if you actually wanted to compute the decay width, as we were talking about earlier, you mod squared this, then the X mod squared you can compute. Okay, but X itself picks up as a phase in it. Okay, so yes.
This stage, there is no connection numerically between G minus
No.
2 and the charge.
No, not at all. At this stage, we don't know anything, and indeed, there had better not be, because depending on what the underlying theory is, maybe I have some higher dimension operator that gives me some G minus 2. I had better not make any such connection. On the other hand, it is nice to, of course we know G minus 2 is very important, but it's more than just important. It's one of the components of the 3-particle amplitude for an electron, right? So it has that completely sharp on-shell meaning. Yes, you had a question. Aha! Excellent. So you see, all of these on-shell amplitudes, again, you could make the same complaint about the massless ones. They don't actually happen in Minkowski space. There's zero, and the same thing here. Okay, so this amplitude in Minkowski space is not there. Okay? But it has a continuation. It's very important. It's crucial that as a general object for general momenta, complex momenta, or in 2-2 signature, it exists. Okay. Yes. Sorry?
How would you actually compute Nima?
I have not talked about how to, here we haven't talked about any dynamics yet. And in this lecture, I probably won't have time to get to it. But if you want the 2-line computation of G minus 2, it's in the paper that I referred to before, using this formalism. Okay? So there's literally a 2-line calculation of G minus 2.
The solicitation on G minus 2, how does it look like?
Just the same thing. We just wrote it down. We could write down something
No,
analogous.
not
Yeah.
structurally.
Yeah.
What would it do?
Well, it corresponds to some higher dimension operator involving EE conjugate R mu nu instead of EE conjugate F mu nu, or coupling to the Riemann tensor in some interesting way.
This G minus 2 is, it's not really G minus 2, it's a constant in front of lambda, right?
Which turns in, which is what is G minus 2. Okay? Yes. That's right. All right. So in general, for spin S, there are 2s plus 1 structures you can have. For a massive spin S particle, with equal mass, say minus, there's something that begins as EMX inverse, and then all the epsilons, epsilon alpha 1 beta 1, epsilon alpha 2s beta 2s, and then there are the lower ones, like the lambda lambdas and lambda alpha, lambda beta, and epsilons plus more. Okay, there are a total of 2s plus 1 structures here that you can have. And that's all we can say. That's all we can say in generality. There's sort of so it's not unique anymore. There's sort of 2s plus 1 moments that you can have. You have the lowest, the charge, or the mass, and then you have the higher dipole, quadrupole, higher moments. Okay? And those are all captured by these higher terms. Now I want to make a comment that from this point of view, of course, we know in nature we don't have elementary particles of spin 17. And you can discover what's wrong if you attempt to have just a single particle of spin 17 coupled to gravity or or with charge. When it's massless, remember, we discovered that it's simply impossible. You can't have massless higher spin particles coupled to gravity, let's say, or charge coupled to photons. If they're massive, you can write down consistently factorizing amplitudes for them. But of course, they should be sick in the massless limit. They should be sick in the limit as the mass goes to 0. So that's one of the ways that very directly you see that you cannot have elementary particles of high spin, which in this context means there's, of course, you and I are particles of high spin when viewed from far enough away, but we have lots and lots of other excitations. There is not a gap between a particle of spin 17 and a huge gap in the spectrum until you see something else. And this is one of the ways you can see that you can't have that, because if you did, you would have these completely sick amplitudes involving the scattering of the massive particles with gravity. Okay, so
But you can have any high spin.
yes, you can have any high spin, of course. You had better be able to, because you and I have large spin. Okay, our elementary particles have large spin. Nonetheless, it is an interesting question to ask. Of all of these 3 particle amplitudes, there was a particular interesting one, or a combination, one of these structures, that deserves to be called minimal coupling in general. Okay, so minimal coupling. Of course, this is going to reduce to the normal notion of minimal coupling, which just means charge, or just ordinary mass, for the low spin particles, but it generalizes it to any spin. And this is simply demanding that the massive amplitude, the massive 3-point amplitude, should go smoothly to the massless 3-point amplitude in the high energy limit for a particle of spin s. Now, what I mean by this is there are many different structures here. There's 2s plus 1 structures. I want to find the structure which, when I go to high energies, I just get the massless amplitude for that spin. Okay, so if I have a spin 10 particle, I want the 3 particle amplitude to be such that when I take the high energy limit, it reduces to the massless amplitude for spin 10. And it turns out that that uniquely picks out this first term. And in fact, if I write this in terms, again, just back in terms of the things with the correct little group indices, just so I don't. Yeah, I just want to write it down properly. No, this is not, again, all of them are allowed. All of them are allowed. We have not said anything about unitarity yet. This is purely kinematics. But purely kinematically, of all these 3 particle amplitudes, there is one that's special, that has the property that when you go to the high energy limit, it just matches on to the massless amplitude in the high energy limit. Okay, so for particle, so if I have this minimal coupling for S and S, and let's say a photon, same for the graviton, trivially modified, but this guy is equal to x times 1, 2 to the 2s divided by m to the 2s minus 1, just for units. So that's for coupling to a photon of helicity 1. So just that extremely simple expression. And for the other one, it's of course x inverse times the other one. Okay, so that deserves to be called minimal coupling for any spin, and it reduces to what we know and love as minimal coupling for low enough spin. Huh?
How is this the epsilon? I mean, where did all the lambda come?
Because remember, we're getting these amplitudes. Just to begin with, for convenience, I decided that I was going to write the amplitude by stripping off all the lambda indices and then contracting. Okay.
Right,
So if we do that, then this is the expression we get. Okay.
The spin S is of the massive particles.
Sorry?
In the massive
Oh, I'm sorry. So remember, these are underlined. Okay. So these 1 and 2 are the massive particles here. Okay. So,
The massless is a general helicity or one?
oh no, this was helicity plus 1, and this was helicity minus 1. If it's for a graviton, it's just the same thing. If it's a graviton plus 2, I just multiply by an extra factor of m over m Planck x. Okay?
And then if 0 would be just 1 over.
Well, no, here I'm giving what the formulas are for coupling to photons and for gravitons. Yeah, if we don't have any spin, we don't have the x. Okay, but, okay. Now, so here I just want to pause and comment that, so we argued what this minimal coupling was just from this sort of simple requirement that the three-particle amplitude turns into the one that we saw before in the ultra-relativistic limit. It's an interesting question. Are there any elementary particles in nature? Are there any particles that we know of in nature of high spin that enjoy this coupling? And the answer is there are. Who is it? It's Kerr black holes. That's quite a remarkable fact. Okay, that if you look at black holes from very far away, of course you look at anything from very far away, it looks like some elementary particle. I can talk about its three-particle amplitude coupling to anything. But the only thing that we know of that has this minimal coupling are Kerr black holes. And so that's of course, which are it's of course not very surprising that the thing which is sort of picked out as a special object from the amplitude's point of view should match to something which is picked out because black holes have no hair. Right? So there's something unique on the black hole side. By all rights, they should have matched up, but it's very interesting that they do actually match up. Okay. All right. Okay, so finally, so this is all I want to say about the three-particle amplitude. You can work out the story for three massive amplitudes, for three massive particles as well, but the main interesting feature is here in the equal mass case with this X factor. And now I want to do a couple of examples of how we compute four-particle amplitudes, exactly the same thing as we did before. Now let's look at some four-particle amplitudes. So let's do, first of all, that example that we talked about. So let's say I want to do photon, as I mentioned before, this is the most trivial of all examples. So let's say I want to compute this amplitude of a photon on the top going to some spin 3/2 excitations of the top, decaying back to a graviton on the top. Okay? So we already worked out what the three-particle amplitudes can be on the left. So this is a trivial case because there's nothing exciting going on. I just have to compute the residue in the S channel and multiply by 1 over S minus m squared. Okay, but now we're just going to work out the residue. So I have to work out what the three-particle amplitudes are. So gamma minus, this one we talked about already. So I'm going to call this intermediate momentum P. So here there are two structures that we're allowed to write down, and one of them, so this is 1, 2, 3, and 4. One of them is P bar 2 cubed. I'll just write them down. Okay, so that's one structure on the left. What about on the right? On the right, actually, there's only a single structure that I can write down because I have a positive helicity graviton. I have to use all these, right? Because I have 3 indices here and 1 here, so I have to have a total of 4 indices. But the graviton already needs 4 V's. So this is just 4 V's. So that's cool. There's only a single structure for massive spin 3/2 coupling to a top quark and a graviton. So on the other side, It's just some G double prime 4 bar 3 P bar 3 cubed. And now I just glue them together. So the amplitude is 1 over s minus m squared for the spin 3/2 particle, multiplied by, okay, so when I glue this one with this one, I have some G double prime. Now, the only thing I want to point out is what happens when I take this P bar 2 cubed, P bar 3 cubed. Okay, so here I have to remember that there were these indices here, right? There are the I indices here and the I indices here. So when so this is a lambda p and this is a lambda tilde p. So when I contract them, what do I get? I get a lambda p I, lambda tilde p I. Right? No, I mean that's just in this contraction I get 3 of those guys. And then, of course, they have an alpha and a beta that are going to talk to other things. Okay? But this is, of course, nothing other than the momentum of the internal guy. Okay? So this first factor, contracting this with this, is just 2 p intermediate 3 cubed. All right, and then I have 1 bar 2, 4 bar 3. Okay, and actually P intermediate is P1 plus P2. So I could write this also, if I like, as just P1. Or if more symmetrically, P1 minus P4. I could write it many ways. Sometimes I like to write it as P1 minus P4. There's a factor of 2, but I won't bother with the factor of 2. Okay? So that's the first term. The second term is then G prime, G double prime. Okay, and this is slightly more interesting. Now I have P bar 2 squared, P bar 3 cubed. So 2 of these indices from the angle bracket P bar will contract with 2 of the square bracket P bar. That's the same as we saw before. That's going to give us the same P intermediate. So one factor is going to be 2 P1 minus P4, 3 squared.
Sorry, why is P1 plus P2 equals P1 minus P4?
It's not. It's that P1 plus P2 is negative P3, negative P4. Okay? So 2 P1 3 is also equal to negative 2 P4 3. So if you want to write it slightly more symmetrically, you'd write it that way, the factor of 2. Okay? Okay, so 2 of the factors are the same. I'm not going to bother with these factors of 2. 2 of the factors are the same, but one of them is just a P bar 2 contract with a P bar 3. Now for that one I have to remember that lambda tilde for P alpha I, lambda tilde, this is alpha dot, beta dot I, this is equal to the mass. That's the determinant. Right? So this is m times epsilon alpha dot beta dot. Okay? So you don't have to do this over and over again. Just once you see it. Anytime an angle bracket P contracts with a square bracket P, it turns into a momentum. Anytime an angle bracket P contracts with an angle bracket P, it turns into the mass. So here we get instead a factor of the mass, m top, times 2, 3. This is the mass of the top in this case, the mass of the external particle. Okay, and then the rest is the same. I have a 1 bar 2, 4 bar 3. All right, so that's it. That's what the amplitude is for this kind of complicated seeming process, but it's completely trivial from this perspective. Yes?
You're using basically only Poincare invariance, right?
Well, here we use more. This is what we talked about last time. Here we're demanding consistent factorization. Okay? So now we're going to write down a 4-particle amplitude, but it has to have the property that has poles in the right spot, and it factorizes on the poles. In this case, for this kind of example, which is the analog of what we talked about last time of the phi cube theory, Yukawa theory, these are the boring, simple examples, because when you glue together The residues, there's no pole. There's nothing funny going on, right? That's why these are the boring, simple examples. You just compute the residue, multiply by 1 over s minus m squared, and call it a day, right? Of course, this is plus contact terms. I can have contact terms as well that we can't predict like this. That's fine, because we also can't predict them from a Lagrangian, right? That's, they have to be there. But this is the part of the answer that has the resonance in it. Okay, and we can completely determine it in this way. Okay? Yes?
Wait,
Yes, sorry. Yeah.
So suppose that I do just a Poincare. I
Yes.
would consider each of these particles as representations.
Right. If you just do Poincare,
The Casimir and the Cartan algebra. So is it just a product of representation of the group?
that's in a sense what we were talking about in our first lecture, in the first couple of lectures here, is what part is pure kinematics. The part that's pure kinematics is using these spin-helicity variables in order to manifest the correct behavior of the amplitudes under the little group. So the most general object you could write down is just something that's made out of these lambdas and lambda tildes. For the massless particles, it has the correct helicity weight. For the massive particles, it just has the correct number of indices symmetrized. That's all we can say just from symmetries. It's already better than using polarization vectors and Dirac spinors and stuff like that, which are very much more redundant representations of the same thing. Notice one more time, no gamma matrices, right? No 4x4 anything. All you see, it's a spin a half particle, so you see two component things, right? It's just as it should be, right? Exactly as it should be. Okay, so I want to do, now the more interesting example, yes?
So here you determine the residue on the pole.
Yes.
But then you use that expression for the amplitude.
Everywhere, absolutely. Excellent, excellent question, excellent point. That's exactly what this is all about, okay?
You also have some other functional dependence.
Yes?
Goes to 1 on the pole.
Yes, yes, exactly. And that's really the point. That all we know from here is that the amplitude looks like this plus contact terms. Any difference in what you think looks, in any difference, any two expressions which agree on the residue will be equal to each other up to contact terms. Okay? We haven't talked about loops. Okay?
Because factorization works also at the loop level.
Factorization is much more interesting at loop level. It definitely does not work in exactly the same way at loop level. That's the problem. We don't know exactly what factorization means at loop level.
My loop amplitude should
Yes.
have the same residue.
Sorry?
My loop amplitude should have the same residue.
Well, no. I mean, loop amplitudes have parts of them have poles, but parts of them have branch cuts, and so it's not just about the poles anymore. At loop level, it's not just about the poles anymore.
It's those poles and other things.
Sorry?
It's those poles plus other things.
You have these poles and you have plus other things, indeed. But huh? The poles should be the same. Exactly. The poles are always the same. The poles are always the same. At loop level, the residue on the pole, at least for these 4-particle amplitudes, it is the same.
Is the reference
Right.
you gave us also talking about loops and the cosmology stuff?
No. The reference I gave you was just for amplitudes, but it did talk about one loop amplitudes in this language as well. Okay. Yes.
You will have, including loops, you will have vertex correction.
That's right, so that's a really interesting question. When you include loops, for example, you will see in QED that you have to have a new 3-particle vertex. You can't just have that 3-particle vertex 0. It has to have a very specific answer. And now you can ask from the on-shell point of view, why is it forced to have that answer? And then we can have another discussion about that. But that's part of the reason I was emphasizing how beautiful it is that G-2 has this completely on-shell definition. It's not something that's slightly ambiguous about how exactly you measure G-2, what experimental situation you do, how you. It has a completely invariant on-shell meaning. Okay, and that's okay. So let's just do an interesting example. Just so we see how the same kind of things show up as we saw in the massless case. So I want to do Compton scattering. So let's do massive Compton scattering. And let me actually do a really simple case first, just of scalars. Okay, so let's say I have a charged scalar. So scalar photon. Right? So okay. So now what I want to do is look at the possible residue in the S channel. And remember, these were really simple. So if I call this 1, 2, and 3, 4, then I'm going to call this guy here mx12, just to remind me that it came from the left-hand side. And this is going to be, let me put a plus and a minus here. And this is going to be emx34 inverse. Okay, so this residue, the residue in the S channel is E squared m squared x12 over x34. Okay, so let's now compute what x12 over x34 is. Remember that x12 is defined as p1 lambda tilde 2 is mx12 lambda 2. Yes, we can. If I can. Oh, here, right, sorry. I forgot about these. So P lambda tilde 2 is equal to m x12 lambda 2. So from here I can derive that if I contract with the, let's say if I contract the left and the right with lambda 3, then I get x1 m x12 32 is equal to 3 p, sorry, this was p1, p1 2. Okay, so that lets me solve for m x12 is equal to 3 p1 2 over 3, 2. In the same way, I can solve for m x34 inverse is equal to 3 p4 2 over 2, 3. Okay, and therefore the residue is equal to 3 p1 2 squared minus sign over 2, 3, 2, 3 e squared, which is minus e squared 3 p1 2 squared. And on the face of it, this looks like t. Okay? So once again, we have the same issue, right? I compute the residue in the S channel because the three particle, now the three particle amplitudes don't have poles anymore, but they have this X factor. And the X factor is the object that has the same, you can't express it, you can't give it a direct local formula. It has the same issues associated with it as the poles for the three particle amplitude had when everything was massless. And again, we see that when we compute the residue in the S channel, it's not local, right? It has a pole in T. And actually, at this point, we can decide how this theory is what kind of. So we have to have something. It's not, just as before. It's not trivial to find a factorizing amplitude. It could be that it could be that we have some underlying theory that actually has a massless particle in the T channel. That would be the case if this was really secretly Yang-Mills theory, and I had a charge W here. Okay? But if I don't have a massless particle in the T channel, if I only have these photons, then I can also notice that when S goes to m squared now remember, this is a massive particle. So when S goes to m squared, T is equal to, now remember, S plus T plus U is equal to 2m squared. So when S goes to m squared, T becomes exactly U minus U plus m squared. Okay, so this could actually also be a pole in the U channel. a massive pole in the U channel. Okay? And so that's the option that we have to choose if there aren't any massless particles in the T channel. And so from here, we directly write down the answer for the scalar Compton amplitude. And again, it's not trivial that it works, but so the amplitude becomes E squared over S minus M squared, U minus M squared, just times this factor 3 P1 2 squared. Okay? We don't have to add. That's the whole point. You see that this is exactly what happened in our massless examples. The deep thing is that we do not add channels. And in fact, we cannot represent the final answer as a sum over channels in a Lorentz invariant way. The answer is not a sum over channels. The miracle is that the residue in the S channel has a pole in the other channel, which is exactly the one needed in the other channel. Okay? And this does not happen for higher spin. It doesn't happen for anything other than Yang-Mills theory and gravity. Okay? And of course, compared to normal Feynman diagrams, we didn't have to, there's no contact term, there's no two channels, there's no contact term that we have to add to restore gauge invariance, right? We just write down the answer. Okay? And I will leave it for you to derive the rest of the Compton amplitudes in this way. But I already wrote down, well, let's just do one more. I think I've already screwed everything up as far as the timing goes, so I might as well screw it completely. Then.
Could you give before the end the reference for the cosmological stuff as well?
Yes, I will. I'll actually sketch something about it, but let's just do this one more example. So let's now we do electron Compton scattering. Electron, boy. Okay, so now the same thing. I just want to look at these residues. Okay, so the amplitude on this, in fact, we can do it for any spin, but anyway, the amplitude on the contraction here is a 1 over, is giving me, sorry, an x12 over x34 as before, but now I have a 1 P4. Okay, that's what I got from minimal coupling. And these are okay, and as before, oh, sorry, the other way around. 1P, P4. Okay, and as before, this is just giving me P intermediate, right? So this is 1 bar P intermediate 4 bar. And just using the P intermediate as P1 plus P2 or minus P3 minus P4, you can very easily write this as M 4 bar 3, 1 bar 2 plus 1 bar 3, 4 bar 2. Over 3 P1 2. That's a very small exercise. That's a 2-line exercise, but I won't do it for you. Okay, and on the other hand, we already worked out what x12 over x34 is. We already computed x12 over x34 is exactly this factor 3 P1 2 squared. Over over T, or U minus M squared. Okay? So the residue in the S channel is now 1 over U minus M squared. Now one of these factors goes away, but is replaced by this one. So we get 3p12 times this guy. And so finally, the electron Compton amplitude is E squared over S minus M squared, U minus M squared, just as before. But now one of these factors goes away and is replaced by the thing that has now the dependence on the massive spinor variables, 4 bar 3, 1 bar 2, plus 1 bar 3, 4 bar 2. Okay? Now, if you continue and do a massive spin 1 particle, W Compton scattering, then it's clear what happens. You lose one more of these factors, and this thing is squared. Okay? And that's exactly the general formula that I wrote down for you before.
Good question.
Yes?
Where exactly did the crossing come from?
Sorry?
Where it did exactly...
We didn't put it in. It's actually forced on you here. That's actually the point. This is how spin statistics comes out. Okay? So if you do the coupling with gravity, that's why it's important to do coupling with gravity, because gravity is a universal coupling. So the logic is you first learn when you have gravity, just by consistent factorization, it must have universal coupling. Good. Now you have something that couples universally. Now you compute the gravity-Compton scattering against any particle of any mass and any spin. And precisely because the answer is not the sum over channels, you can't choose what the statistics is. You either get the right answer or you don't from one channel. And the answer that you get forces the correct statistics on you. And crossing. Okay? More generally, crossing is not a consequence of it. Crossing is a deep fact. Crossing is not a trivial fact. And it's barely proven in quantum field theory.
Right.
So it's not...
comes out for free? Or?
At this tree level, yes. Yeah. So I mean, crossing is relatively trivial at tree level, even in field theory. It's more complicated at loop level. But here it's really spin statistics ultimately that's coming out from these arguments. But indeed, I mean, if I want to stress one point over and over again, we see from this way of thinking about things exactly what's so special about theories of massless high spin particles, massless spin 1 and massless spin 2, that they're not thought of in a channel by channel way. Okay, that's a sort of a deep fact about them, and it's reflected in the amplitudes. The amplitudes have this product structure, not a sum structure. That's also a very stringy thing. We're used to the idea in string theory that you don't get the sum over channels. That sort of one thing, and it's not accidental. The product structure is remarkably there in string amplitudes as well. For an open string amplitude, you get gamma over gamma. It's a product, not a sum. For gravity, it's gamma over gamma. That's how you get a 1 over STU downstairs. Okay, but that's not some magic stringy thing. In fact, it's just generalizing this amazing fact about the massless amplitudes for photons and gravitons to begin with. Okay. Okay. So, all right. So that's it. I have 5 minutes to give half of my lectures. But let me just say a little bit about the analog of this story in cosmology. So actually, maybe let me just pause though. Any questions about this? So what I wanted you to see is that first, how these sort of basic and deep facts about the way the world works. We've really concluded basically directly from relativity and quantum mechanics that in the massless limit, the world is ridiculously constrained. It has to look like the theories that we know and love. You're allowed to have massive particles, but the massive elementary particles can't have spin that's too large. We worked out a bunch of amplitudes. There's just 1 or 2 examples we have left that we could talk about. Like, can we have massive spin 1 particles? And then if you continue the sort of logic, you'll discover that you can have them, but they would screw up in the ultraviolet unless there's the Higgs mechanism, and you will discover the Higgs mechanism from the top down in this way. You ask, can you make sense of massive spin 2 particles in the same way? And the answer is no. You can't Higgs gravity in the same way that you can Higgs massive spin 1. So the kind of 0th order picture of what the world can look like from this point of view. Say if it's massless, it's nailed. If it's massive, you can have some massive particles, but not with spin that's too large. And starting at spin 1, there has to be something like a Higgs mechanism, but not for spin 2. And you can also have a massless spin 3 halves, and those can also be Higgs okay. All right? That broad brush level of what the world can look like is basically a consequence of these simple algebraic arguments about factorization about Poincare invariance nailing 3 particle amplitudes and consistent factorization for 4 particle amplitudes. So it's conceptually very beautiful, but I was also trying to explain to you just practically how to do calculations like this, because I also want you to see that it's we not only learned conceptual things, we also wrote down the answer. So we discovered that the Compton scattering is consistent, and we wrote down the answer. We discovered the graviton scattering is consistent, and we wrote down the answer. Okay? So this is, as I said, this is the totally responsible part of the subject. There's a more exciting irresponsible part of the subject, okay, where you actually start making guesses for more complicated amplitudes, or you try to forget about locality and unitarity and ask other questions and see that these answers come out anyway. But but already the responsible part is interesting enough, and that's what I wanted to talk about in the first half of my lectures. But let's just pause. Are there any burning questions about that before I speak for 5 minutes about cosmology?
Well, the statement that you made is only the elementary, but bounces you can have at any spin. So
well, you even discover that. You see, you even discover you're allowed to have. Of course, there's no problem to have bounce states, but you cannot have a large gap between them. No problem, exactly. But there's nothing wrong with that, of course. But you discover that you cannot have a spin 13 particle and a parametrically large gap before you see other things. So that's the distinction between composite and elementary. And even the distinction between composite and elementary you can discover from this point of view. Okay, right? Yeah, no, right, but it's not obvious without relativity that you couldn't have that anyway. Yeah, yes.
Can you get any insight into hadronic processes from
Well, I mean, I think probably the most useful thing is just the most useful thing is these is the ease of just writing down all the allowed structures for 3 particle amplitudes that you can use for decays. Okay. Beyond that, if you want to do 4 particle processes, it's not particularly weakly coupled. So it's not weakly coupled. The sort of course, you can work in some pole approximation, and then you might get something useful. I don't know, but probably the most useful thing there is just as a simple way of classifying, writing down all the allowed 3-point couplings, which I'm sure it's possible in other ways as well. This is just an especially simple way of doing that. Yes?
You have a spin 1 particle mass, you say you discover the Higgs mechanism.
Yes.
Can you find other mechanisms like Stuckelberg?
What Stuckelberg is not a mechanism. That's the point. The Stuckelberg has no content. And so you discover it has no content because there's nothing there. You just write, when you have an abelian theory, there's no difficulty with the amplitudes of the longitudinal components, and so you write down the amplitudes and everything is fine. So you don't need to say the word Stuckelberg. Everything about gauge invariance, Stuckelberg is the thing that is most convincing about how content-free it is, because you take something that's not in gauge invariant and you make it gauge invariant by introducing something. But from this point of view, you never need to do it. Yes?
For the method casting, there are some existing relations to construct
That's a good question. They're being developed. So it should be possible because what makes these recursion relations go is some good behavior of the amplitudes at very high energies, and at very high energies the mass should not matter. But technically, a few of them have been written down, but has not been developed a lot yet. So that's something to be developed. Yes.
Is there a nice story about anomalies in this language?
There is a nice story about anomalies in this language, but for that, of course, we have to talk about loop amplitudes. So the story about anomalies is that in chiral theories at one loop, the amplitudes that you completely determine by unitarity have a pole that you're not allowed to have. And so, and in fact, you not only learn about anomalies, you discover the Green-Schwarz mechanism at the same time. So in 4 dimensions, in 4 dimensions, you discover the particles got to become massive. In higher dimensions, you discover the Green-Schwarz mechanism. In other words, as the only way to give a unitary interpretation for the one-loop amplitude that you computed. Yes.
So can actually actually the method deal with the non-flat loop?
I mean, it depends what you mean. That these are the variables the amplitudes actually depend on. I mean, it has nothing to do with formalism. You can even use ordinary Feynman diagrams if you like. But if you wanted to use ordinary Feynman diagrams, at the end of the day, you would write the polarization vectors in terms of lambdas and lambda tildes, and the actual amplitudes are functions of these variables. That's just true. That has nothing to do with a formalism. That's just true. There's then a question, can you determine the amplitudes? I mean, here we determine tree amplitudes, the simplest 4-particle tree amplitude. You can determine one-loop amplitudes for any theory. Okay? It has nothing to do with planarity. You can determine 2-loop amplitudes are the frontier of trying to figure out what the set of functions is with the correct branch cut properties to capture general 2-loop amplitudes. But non-planars are being done daily in this business. I mean, the sort of planar ones have been understood for a long time. So when I say the 2 loops is the frontier, it's the sort of frontier for understanding the generic non-planar ones. Many non-planar ones have been understood. Okay? But I want to stress that you know, the fact that this subject is stuck in perturbation theory just reflects the depth and difficulty of the problem. Right? We're trying to understand something extremely basic about how causality is reflected in the analytic structure of scattering amplitudes, and we don't know the answer to that question. The only method we know to start getting a clue, at least the most direct way, the least adventurous way, the most direct way, is to just look at what graphs look like and see the analytic structure that we get from them. And that's what people have been doing. And it's extremely rich, huge amount of structure. And already this question starts connecting to fascinating aspects of algebraic geometry. You know, that there's an enormous amount of mathematical structure in this question of what the analytic structure of the amplitudes looks like. So it's not some trivial exercise. You just have to work very hard. No, I mean, there's a lot going on that you have to try to understand. But the sort of simplest, the sort of planar graphs have been understood for quite a while. I mean, the last 5, 6, 7 years, and when I say that there's a 2-loop frontier, it's really sort of the more complicated 2-loop graphs with masses on the inside and so on, which are the things that people are trying to understand now. There was another question. Yes?
Since you're not using loss picture in this point of view, there's no RG. If I have an IR theory and a UV theory, how do I relate this to in the context of amplitude? Well,
I think we shouldn't mix up different things. One of them is that in any old theory there are in any old theories where you care about amplitudes, there are amplitudes. They depend on these variables. They have these sort of factorization properties. They have the analogues of these factorization properties at loop level, and you should try to understand them. There's a separate question, which is all of these factorization methods are about long-distance singularities, one way or the other. You know, when a bunch of particles go on shell, or some singularities involving infrared physics. Of course, the entire story of the RG is about the Euclidean ultraviolet physics. And so you can ask whether we can sort of effectively capture that. In the end, if you're computing the amplitudes one way or the other, you're getting it. But the question is this on-shell way of thinking organizing the way of thinking about the amplitudes in an easy way to understand the ultraviolet renormalization group? At the moment, we don't know the answer to this question. So this seems to be the biggest challenge, at least to me, conceptually in this subject, is to understand the renormalization group from this point of view. If you just want to compute something, compute the one-loop beta function, then you can compute the one-loop beta function in 3 or 4 lines. Okay, so the computations are always easier from this perspective. The practical computations are trivially always easier from this perspective. But the conceptual questions about why a 100-loop leading ultraviolet log is determined by a one-loop calculation. Now that's something which I have no idea how to begin approaching that question from the on-shell point of view. But of course the Wilsonian point of view gives us an immediate answer. Okay? But it's not for a trivial reason. It's for a sort of a deep reason that the Wilsonian picture is Euclidean and off-shell. Here this is dynamical, Lorentzian, and on-shell, and they're manifesting different aspects of the physics. Okay, yes?
What will change if we replace flat Poincare by ds or ads?
Well, that's the topic of the second half of my lecture. So maybe I'll take that invitation to say a tiny bit, and then we'll. These guys did a brilliant thing by putting my colloquium right after my lecture. So to put she's learned well. My Padawan learner. Okay. Okay. So let me just say a little bit about the analog of these things in de Sitter. So I'll just say some qualitative facts, kind of an invitation to the subject. So we started off by saying that amplitudes are the kind of objects that we care about in particle collider experiments. They're more conceptually, they're like an observable that lives on the boundary of space-time in cosmology. Cosmology is the ultimate historical science. Okay? And any historical science has an interesting relationship to the notion of time. We talk about the early universe, but none of us were around in the early universe. No one was there, no experimentalists were there. So cosmology is an observational science, not an experimental one, right? So unlike particle physics, where we get to do experiments over and over again, we get to control the initial state and see what comes out. We can't do that in cosmology. None of us were around. The experiment can't be repeated. It happened once. And so what do? We sit around here and we look at patterns in space. We look at patterns in space, and then we infer the existence of a cosmological history to give a rational accounting, a simple rational accounting for that pattern of correlations that we see in space. And this is what every historical science does. Just that cosmology is the most glorious one. But paleontology, they say dinosaurs exist. We weren't around when dinosaurs existed. Why do we say dinosaurs exist? We say dinosaurs exist in the past in order to explain a pattern in the present, that if you dig in the ground, you see some bones that look like big teeth, and maybe inside the big teeth there's some smaller bones, right? There's a big dinosaur and a smaller dinosaur, and we all says that be yesterday. The bullet, experiment. Talk about our give get two take in order to get a don't know do it and okay, and honestly, zero. There is a picture. Uh, we're measuring. That what we're really measuring, that's now to imagine that this is minus the eta squared. As we Hubble as kind of a what we do is we have to now there, but then they're function just the dynamic contains for instance, functions up. You this is one. So that's a zeroth And you approximate certain kind of non-Gaussianity. Very this instead so because it's a total this work energy 1 plus energy theta. But the an amplitude that delta 3 plus E4. So that's the difference that I just to get. We don't we now negative values of this energy. on that pole, you know, there are similar normal blocks, invariant compute oscillators without any way. Okay? The in the case and it is. That's just for the scale side. Even the presence of massive pair produce but if these up function between